A new car is bought for 28,000 euro and depreciates in a value every year by 17%. Represent the depreciation as a sequence. In other words, write out the equation for this guy. We could talk about this because it says as a sequence. So for a geometric sequence, that would be a sub n equals a sub 1 times r to the n minus 1. So that would be a sub n equals, the initial amount was 28,000 euro. So that means that at the end of the first year, so our a sub 0 is 28,000. So our a sub 1 is going to be 1 year later, which is that 17% decrease. A 17% decrease from 28,000 would be 100% minus 17 is 83%. So, sorry, I know some of you are visual. I'm visual. 17% decrease of 28,000 is equal to 0.83 of 28,000. So that means that we took the 17% and subtracted it out from the total, which is an 83% of that initial amount. So at the end of the first year, our first term in the sequence, the value of the car is 23,240, and that will be our a sub 1. 23,240. Our interest rate is 0.83, as we've talked about. To the n minus 1. And that is the situation as a sequence. It gets a little bit more complicated than that if we wanted to represent it as a financial compounding interest type of problem, but that is it as a geometric sequence. You can do both because they are interchangeable. There's just, when we start dealing with compoundings, that's when things get interesting. Okay, how much is the car worth after 5 years? So we could plug in 5 into this equation. 23,240 times, so we want a sub 5 so to the 4th power. And we get 11,029.30 euro. Assuming the car is maintained properly, after how many years will it be worth 9,000 euro? Okay, so we then now are starting to deal with our exponent being the unknown. And in order to solve for an unknown in an exponent, we have to use logarithms, which I know some of you feel pretty confident with, and some of you don't. If you don't, oh my goodness, your calculator is your savior, okay? So you can use the problem solver in here, the numerical solver in here. You could use the financial solver to solve for this by plugging in what you know. You would not be plugging in 23,240 as your present value. You would be plugging in 28,000 euro as your PV in your financial solver. So you can use your calculator in so many different ways. You could also set up this equation where it's 9,000 would be your result equals 23,240 times 0.83 to the n minus 1, right? So we've just made that equation. And if worse comes to worse, if you ever get to this point on a test, set both sides equal to y equals and find where they intersect, and you should still be getting the same answer. Okay. If you would like a recap, I'm going on how to solve for, actually, no, I'm not going to recap how to solve for this algebraically, because that's silly when you have the whole world at your disposal through this calculator. I am going to use my financial solver, however. My number of years is unknown. It's a percentage decrease. So I'm going to do actually negative 17 in my percentage instead of 83%, although you could do either one. My present value, I'm going to do my initial of 28,000. My final value, I want to be 9,000. No compoundings. I want to solve for number of years. And we should get 6.09. So 6.09 is the answer for n here. However, of all of the ways you can use your calculator to solve, there's so many. 6.09 should be the answer that you get, which means 6 years. After 6 years, it'll be worth 9,000. Quite a dip from 28,000. Use the graph of the sequence to display and discuss the depreciation pattern. Okay, so our calculations, our final value, or y equals or whatever, is 23,240 times 0.83 to the n minus 1. I'm going to go ahead and graph that on my calculator. Remember that the variable is in the exponent, which means that it is an exponential equation. Remember that idea of something growing exponentially when we were talking about functions and models and what it looks like for something to be growing exponentially is where it just all of a sudden shoots up. And people use that word all the time where they're like, oh, it's growing exponentially. And I want you as mathematicians, because yes, you are all mathematicians, to think about it analytically and say, is it really exponentially? Because it's not. Most times, more often than not, when somebody uses that word, they're just saying, oh, it grew a lot. Growing exponentially is way more extreme than growing a lot. So people using that phrase should stop using that phrase. Don't use that phrase. Okay, so I am graphing this. And it looks crazy because my zoom is crazy. So I'm going to zoom in to a more standard zoom. Actually, the zoom was not crazy. Oh, yes, the zoom is crazy. Hold on. Zoom, I'm going to go to standard first, which is what I tell you guys to do all the time, and then zoom out. Megan, why don't you listen to your own advice? I don't know. Okay. I hope that you have gotten to the point where you can see it. You've zoomed out a few times. The graph looks something like this, where it really does drastically just like come down. And I want to show you that like that number right there is 40 or something like that, to a value of like 14. But anyway, it's got this idea of where it's going down, and then at some point it tapers off. So it says, use the graph of this sequence to display and discuss the depreciation pattern. So the depreciation pattern is that it sharply decreases in value. I'm going to say this and not write it out because writing on this is really not easy for me. I should stop complaining. I'll just write it. Okay, so it sharply decreases. But at some point, tapers off. Remember using that phrase with exponential equations? And the reason why is because we do live in a consumerist world, maybe not in a consumerist society or government. But we do live in a consumerist world where we do want to go out and get the new iPhone every couple of years. We do want to go out and get the new season's worth of clothes or get the newest car that's on the road. And so the way that people out there who are deciding values of things are manipulating us is that they're telling us that after a certain amount of years, the thing that you own doesn't have the same amount of value anymore. It is somewhat of a construct of our making, but that's just kind of what it is. But at some point, there's this other piece that comes into play is that everything that you have has some sort of value at some point, whether it's a car and it has parts that could be used for somebody else's car and that has value that you could charge for, or whether it's clothes that you could sell to somebody else at a discounted price if you wanted to go to what are those stores called where like it's like they're boutiques of sales of used clothes. But there's definitely everything that you own has a certain amount of value, and there's a value of it as a part or of something or as a remembrance of previous history, that at some point that value overrides the value of it in a consumerist society, and that comes into play as this cost tapers off. It will never be negative. You'll never pay somebody to take a car away from you. Maybe. You'll never pay somebody to take these clothes away from you. Maybe, right? But you will always have some sort of value there left with whatever the thing that you own is. And so something along those lines should be brought into discussion when you're talking about this graph, that there is this play of things lose value over time because of the societal constructs that we have, and the governmental and economical and all of those things that come into play for benefit or for detriment. But also the things that you own have a value in some way, shape, or form at some point that supersedes all other consumerist agendas. That makes me sound like a really big conspiracy theorist against consumerism. I'm definitely a consumerist. I buy new things. It is what it is. But yeah, okay. That's all I have for you today. You have homework that deals with interest. Good luck.